Welcome back, everyone. In this lecture, we're going to discuss cost functions. We'll now explore how can we evaluate the performance of a neuron. We can use a cost function to measure how far off we are from the expected value. So we're going to use the following variables and notation. Let's quickly review this so you don't get confused when we actually see the cost functions. We'll use the variable y to represent the true value, and we'll use the variable a to represent the neuron's prediction. So what does this actually mean in terms of weights and biases? Well, remember that we said w times x, that is the weight times the input plus the bias, is equal to z. And remember that they pass z into the activation function. So for example, if we're using the sigmoid function, we could say that sigma of z is equal to a, so that neuron's prediction. When we actually put in the sum of those weights times the inputs plus those bias terms, we get this z, and then we can pass that in to the activation function, sigma of z, and that is equal to a, which at the end represents the neuron's prediction. So the first cost function we're going to discuss is the quadratic cost function, and that is equal to the sum of y minus a squared divided by n. And you can, if you want, pull out 1 over n. So what do we actually see here? Well, we can see that larger errors are more prominent due to the squaring, because remember, y is that true value and a is our predicted value. So if there's a big difference there, when we square it, it's going to really be prominent. Now, unfortunately, when you actually implement this quadratic cost function, this calculation can cause a slowdown in our learning speed due to the way that formulaically it actually works. So instead, we're going to be using cross entropy as our cost function. And this is defined in the following manner. We say negative 1 over n, and then we take the sum of y times the log of a plus 1 minus y times the log of 1 minus a. And this actual cost function allows for faster learning. And the reason for that is the following. The larger the difference between y and a, the faster the neuron ends up actually learning due to this cross entropy cost function. So that means that if we end up at the beginning with a really large difference between our predicted value and the true value, we can essentially quickly jump forward using this cost function, because the larger that difference, the faster the neuron's going to learn. So now that we have these two key aspects of learning with neural networks, the neurons with their activation function and the cost function, we're still missing a key step, and that's the actual learning process. So we need to figure out how we can use our neurons and the measurements of our error, our cost function, basically a measurement of how wrong we are, and then attempt to correct our prediction. In other words, actually learn. So again, so far we understand the neurons, the perceptrons, how we can link them together to get a neural net, and then we also understand now that we have these cost functions that are essentially measurements of how off we are, how wrong we are, what our error in general is. So now that we have these two key components, we need to understand, well, how do I actually fix that error? And what we're going to do is in the next lecture, we're going to briefly cover how we can do this with gradient descent, which is probably a term you've heard before if you've ever read anything on machine learning. Okay, let's go ahead and discuss gradient descent in the next lecture. I'll see you there.